In the next few lectures, we're going to talk about concentration, and hopefully this is review. We're going to introduce something new called molality, though. So let's first review with what concentration is. So it's going to just be the given amount of a solute in a solution. So when we make solutions, we can make them in a lot of different ways. We can choose the amount of the solute we want to have compared to the amount of solvent. So that ratio is something that we can control within the limits of solubility. And so concentration is not the physical property of solubility, which is how much will dissolve, like what's the maximum amount of sodium chloride we can get into 100 grams of water, but it's what we make up in the lab. So this is something that you have lots of different types of units for representing, but let's walk through the process of making a solution and talking about what the concentration will mean. So this is a volumetric flask, and it is fantastic because it has only one measurement marking. And that measurement marking on this one is right here. It's just a little line, and it's a piece of glassware that is designed to just do one thing, and it's to measure one volume. So in this case, it's, I think, probably we'll assume it's 1 liter, right? Yeah, it's 1 liter. And so what I would do to make a solution is I would calculate the amount of my solute I would need to make the concentration of my choice for a total volume of 1 liter. And that would be the volume of the solution, which is always in the denominator of our solution concentration calculation. So I would weigh out a mole of sodium chloride, which is going to be like 58 grams, and pour it into my volumetric flask and then add water until it's about like half, 3/4 of the way. And then I would stir and stir and stir, or swirl and swirl and swirl, or shake and shake and shake until it dissolves. And then I'm going to add water again until I hit that one marking, that fill line for 1 liter. And then I have a really exact measurement of the amount of the solution that I have, which is great. Um, and I've been able to weigh out my mass of my solute, usually out to at least 2 or 3 decimal places. And so I can get pretty accurate concentrations. So this would be how you would make a 1.00 molar solution of sodium chloride. So the keys here to concentration is that we typically represent it as a ratio of the amount of the solute to the amount of total solution. When we do things like molarity, which is a common way that we characterize concentration, especially in a chemistry lab. That's kind of our go-to because we care about the number of particles. So we care about the number of moles that we have of something that helps us predict the products we'll make using stoichiometry. And so molarity is going to be the amount of solute in moles for our units divided by the total volume of that solution. And we always have it in liters. So it's always moles per liter for molarity as our units. But here's the interesting thing when we're talking about volume of a solution, especially volume of water, is that that can change with temperature. So density is a physical property that is temperature dependent. And if density is temperature dependent, then that means the volume of something of a liquid like water will change as we increase the temperature. And thinking about this kind of like in a microscopic view or like a little bit more molecularly, like if we have a liquid and we have these little particles moving around, tumbling all over each other, if we increase the thermal energy, the temperature, we're really increasing the kinetic energy of that system on average. And so these particles on average are going to be moving faster. And so they're going to have more of that translational motion. And the faster they're going, it can create more space, right? And so we'll see them tumble around and change that volume that they occupy slightly, very slightly. You and I would look at the volume and like a naked eye would not be able to see the difference, but we would have a variation in how we calculate or we'd see a variation in our calculation. So here's an example. We have saline solution, which is 9 grams of sodium chloride per 1 liter of H2O. And so I could calculate my molarity here. It's kind of coming back to molarity. Sorry, I went on a density tangent. So I'm going to convert my 9 grams into moles using molar mass, and then put that number of moles here at the top of my fraction for molarity. And then I'm going to put the total amount of my solution right here on the bottom in liters. And it'll get me a 0.154 molar solution. So that's how we've been typically managing or calculating concentration to date, and what we use a lot in the lab. But whenever we have to take into account temperature changing and that concentration is important, we need to use something that takes into account that temperature dependence of density and volume. And we call that molality. And I get that this is going to be a little frustrating because I know it is for me. Molarity and molality sound so similar. And when you write them out, they look the same. And you're going to love this. The variable that we use to represent it is still an m. It's just a little m. And so that's frustrating. So here I'm gonna write them out side by side. So comparing these for molarity, we have a big M and we have moles per liter. Molality will be little m and it'll be moles per kilogram. So instead of measuring the volume, we'll measure the mass. But instead of we won't put this ratio of the solute versus solution. Instead, we're going to look at just the mass of the solvent. And so the mass of the solvent rather than the mass or the volume of the solution total. So this is kind of a direct comparison to the components that make up a solution rather than a comparison of one component to the total solution. So be aware that this can be confusing. Like it could be kind of a jumbled mess because there's a lot of similarities. In terms of remembering the differences between these two, molality is something we use way less. So typically when we talk about concentration, we're always talking about a solute amount relative to a solution. Unless temperature's all over the place, we need to employ molality, and then we'll just do solute to solvent. And this helps solve for this temperature dependence problem because mass is going to be temperature independent. So as we increase and decrease the temperature, our mass of our solvent, of our water, isn't going to change the way our volume will. So here's an example of how to calculate the molality for that same saline solution we looked at for molarity. So our saline solution was 0.154 moles of sodium chloride in every 1 liter of water. And so this is going to be different in a way from the problem that we did. So before we looked at 1 liter of solution, here we're saying we have 1 liter of water for our 0.154 moles of sodium chloride. So we're talking about a different amount of water, a different concentration. In our previous problem, we used 1 liter volume of solution, and we had like 60 grams, almost 58 grams of our sodium chloride. And so just like back of the napkin ballpark estimation here, that means that our sodium chloride might have occupied up to like 28 or 30 milliliters of volume. And so our volume of water was probably more along the lines of about 0.7 liters, really roughly. So we're talking about a different amount of water. So quick note. So in this case, and I'm using the 1 liter to simplify our calculation. So if we had a liter of water, we would need to use its density at the temperature to determine the number of kilograms we have. So here's actually our density right here. This we're going to need to look up based on temperature. It's typically around room temperature-ish. It's about 0.999 something, or about 1 gram per milliliter. So 1 gram per milliliter would equal 1 kilogram per liter. And that's just kind of multiplying both of those by 1,000. So my 1 liter of water, we're going to estimate at 1 kilogram of water, and we'll input that into the bottom of our equation. And for our solute amount, we'll go ahead and put in the number of moles we have. So both molality and molarity have our solute units in moles. And what's changing is just how we characterize the solvent or the solution. And so this would get us a 0.154 molality sodium chloride. And we'll do a more direct comparison in one of our practice problems. So here are our other types of concentration that we typically use. Less in the chemistry, although no, in the chemistry lab too. In general, the way that we characterize these ones is with this kind of generalized formula that we either have the mass of the solute versus the mass of the solution times some sort of multiplication factor, or we have the volume of a solution versus the volume of the volume of solute versus the volume of a solution times some sort of multiplication factor. And that'll characterize all of the ones that we see here. That multiplication factor will be 100% for percent mass per mass or percent mass per volume. There's also percent volume by volume. And we'll see that multiplication factor be 10 to the 6th for parts per million or 10 to the 9th for parts per billion. But for all of these, we're still looking at the mass of the solute versus either the mass or the volume of the solution. And so that's kind of a key piece of this, is that this denominator is always relative to the solution, just like molarity, but not like molality. The other way that we have characterized concentration so far, that is hopefully a review, is mole fraction or mole percent. So a mole fraction is usually you can do it versus the represented for the solute or for the solvent, but it's like one of the components of the solution versus the rest of the solution in terms of moles. And so we get something that's the amount of, in this case, solute, because we're looking at the mole fraction of solute. We'll characterize that by the number of moles divided by the total amount of moles that we have for our solute plus our solvent. So again, this is really the moles of the solution right here, right? Following this pattern of comparing a component of the solution to the total solution, just like molarity, just like percent mass per volume or mass per mass or volume per volume, but not like molality. So here's an example of this one. And sorry, I'm noticing that the S here did not get subscripted. My apologies. And mole percent is going to be that mole fraction of solute just times 100%. So it's the same representation for concentration. It's just representing it as a percentage rather than a fraction, so a decimal. So in this example, we have a gas mixture that has 2.67 moles of oxygen, 7.05 moles of nitrogen. What's the mole percent of oxygen? We use this to characterize these mole fractions a lot in gases, and that's where we saw this before, was in gas behavior. So looking at our mole fraction of oxygen, we have our total moles of our solute. Since we care about the oxygen, we're going to put the oxygen moles on top. Now we need to do the total at the bottom. And so it's going to be that moles of oxygen plus the moles of our nitrogen that we have. And that'll give me that mole fraction. I'll then just multiply that by 100% and I'll have my mole percent.